Hello. Just before lunch, Saturday, October 21st, 2023. This problem took me a little back because I know the j-invariant is a modular function, not a number given by an elliptic curve, so I had to look a little into it. I took some formulas from the book and believed that then this should be the j-invariant of an elliptic curve given by this. I had to understand it a little when we are in another context like this, where y squared and the sum minus 1 divided by n. What would it be in this case? And I guessed when we have the standard form we get from the elliptic curve, the discriminant of this is here, and g2 divided by the discriminant, that's the j-invariant apparently, or the cube, g2 cubed. All right. Then I tried to I don't know what I tried here. Then I tried to do the same with a polynomial of this form, and I divided the discriminant by 16 because then the result gives something that looks reasonable, and that was exactly what I found by this in this paper from Stanford University. Here we have the formula 4a to the cube, exactly what I got here. So I was ready to start on the problem using this formula, but now I've started. It was actually a paper on complex multiplication, so I looked into a little into that as well, but I don't think that's relevant. Now, we do have another guy here, so this j-invariant requires that we have number 4 here, which we don't, so I'll have to find the guy when we have 1 divided by n. So we'll just do the same here. Copy this guy. And then put an n on here. Oh, it should be 1 divided by n. And then this is what we get. Actually, I will insert what we have here. This was lambda minus lambda inverse divided by n, and this was minus 1 divided by n. I'll just check that. My God. Oh, it was the opposite. My. So when lambda is equal to 1, this is what I get. A, what's that? There should be no A. Oh, that's the wrong guy. Oops. So, oh yeah, when we have this, then it vanishes, of course. I would like to expand this guy. Here we can factor 4 out, and here we can factor n out. So the fraction we are interested in is divided by this, and then to factor 4, n divided by 4 out. Simplify. So it's so nice to factor. I will make a pause while I copy that to the page. We have to show, so here the answer was naught. We have to prove that no other rational value give integers. Well, actually minus 1 gives naught as well, according to this. Obviously. course that gives the same equation. Well, well, well. I guess this is as far as I can make it now. Hello again. I've had my living room repainted, so 3 days paint job done on it. It's finished now, Thursday the 26th of October. I couldn't help looking at this problem, and I discovered I've committed a terrible mistake here. It should be x squared and times x. I looked a little more on the j-invariant and complex multiplication, mostly because I wasn't sure if I should be able to prove this with the knowledge we already had. I didn't really know what complex multiplication meant, but I found this lovely paper by Koblitz. It's actually rather complicated, and I found it contains this section on complex multiplication. You see, my problem was if we have complex multiplication on an elliptic curve, does it come from a complex multiplication of the lattice? That was far from clear to me. And this is the key point I don't get. Any endomorphism of C modulo the lattice when we just look at the map of the origin, then it is multiplication by a constant alpha. That's really not clear to me. Now, if the lattice, for instance, is a square, generated by 1 and the imaginary unit, how about taking the conjugate of z maps to z conjugated? If we then multiply by the imaginary unit itself, it mirrors lambda. Doesn't that give a complex multiplication in, well, I don't know, but then on the other hand, complex multiplication that's not clearly defined. Well, it is, but I can't limit the possibilities. Well, I had to live with that. The next thing was the j-invariant. If we write the polynomial in this form, what is the j-invariant then? And this is the form. It doesn't come out well. Well, this is the formula that I already guessed from the data in the book. Having found this error, I first wrote the equation, then we translate so that the coefficient to x squared vanishes. Collecting in terms of x, we see we have x cubed, x to the first, and y squared, and then this. Then we scale x and y and multiply by 4 divided by n cubed to get this equation. and we have then I squared equals 4x cubed minus this times x, and then this constant, of course y squared, needs to be taken out of that. So it has the right form, so we can read out g2 and g3, insert it in the formula, and then we get this expression that we shall prove if lambda is rational will have no integer values. I wanted to check that this was, that if I made a transformation to the form x cubed plus ax plus b, I would get the same result. I did that down here, and we end up with the same j-invariant. And it's actually not so difficult to see from this formula. Because if we use y mark equals 1/2 y, and like the substitution, we get a factor 4 on all coefficients. And then we take it out here, and well, then so it's obviously the same formula. Right. We need to check whether this can become an integer. We may assume P and Q have no common prime factor. Let's take a prime factor in Q. If that divides this expression, then it divides this, but it will also divide the the last two terms, meaning it will also divide P. Contradiction. And that means all prime factors of P and Q divide 2 to the 8th. And they can't be to both of them, so one of them must be unity. And since P to the 4th must divide 2 to the 8th, we can have no more than 1, 2, and 4. So we just need to call this something. And then compute those values. And the funny thing is that 2 and 1/2 will give the same result. So actually we could just do it on J itself. That's more easy. And we only need to take 1, 2, and 4. So let's go 1 to 4. And we see we do get an integer here when I is unity. That's the case we know. Let's just check my theory that it gives the same. It does indeed. So that solves problem 10, but I still am mystified somewhat with respect to complex multiplication.